So next speaker will be James Naughton. He will present a paper, Optimization Multi-Energy Virtual Power Plants for Providing Multiple Market and Local Network Services. James is a PhD student jointly with University of Melbourne and University of Birmingham, so Australia and UK. Before his PhD, James received his Master's in Engineering, Electrical Engineering from the University of Southampton in the UK. His research focuses on modeling and operational multi-energy virtual power plants and how virtual power plants flexibility could be used to provide grid services and maximize revenue by value stacking. So, James, I can see your presentation, and I think you should be
great.
Good to
Can
go.
you hear me?
Please. Very well, please. Thank you.
Fantastic. Okay, thank you very much for the introduction. So today I will be presenting the work done by myself and my fellow authors on the optimization of multi-energy virtual power plants for providing multiple market and local network services. So we are moving from a grid where flexible generation is dispatched to match inflexible load towards a system where a large part of the generation is more inflexible, such as renewables, and the flexibility in the network comes from loads and distributed energy resources. The traditional thermal generation was also providing technical services to the grid, which now renewables are less able to provide. So these services must be sourced elsewhere. Due to their size or technical limits, individual distributed energy resources may not be able to provide network services. But aggregating DER into a virtual power plant enables them to provide such services. Consideration of active power services allows a virtual power plant to assist in grid balancing through services such as frequency control ancillary services, or FCAS, whilst controlling reactive power can allow the VPP to provide local network support, particularly surrounding network voltages, which face particular challenges from rooftop PV. This type of service is becoming more important with the increase of DER causing reverse power flow in networks. Considering multiple energy vectors within the virtual power plant can increase its flexibility, allowing it to better provide services, but also provide additional revenue streams to better the economic viability of a virtual power plant. So, quick definition or how we define a virtual power plant. A virtual power plant aggregates and coordinates a generally diverse set of devices to be seen by system and network operators and to act in energy markets as a single entity. When these devices lie within a local area of the network, they can be controlled as a virtual power plant to provide local network support in order to help locally maintain network voltages and avoid line congestion. With the proper consideration, a virtual power plant can also operate in multiple markets simultaneously, operating to maximize its revenue while minimizing its operating costs. So the operating framework proposed in this work functions as the control center in this diagram, and so needs to be able to consider a wide range of devices, as well as a range of markets and services that operate within the network. So this framework optimizes the operation of the devices it controls by scheduling and dispatching them. And to be able to provide additional services, optimal power flow equations also need to be considered. We're looking at this work in the context of the Australian system, which has a 5-minute dispatch interval, so the framework needs to be able to handle that. And consideration of energy storage means that there are intertemporal constraints, and so the optimization needs to be considered over a horizon. And due to the cyclical nature of loads and renewable generation, a 24-hour horizon makes the most sense. The optimization also needs to consider uncertainty in load, price, and renewable generation to ensure that the virtual power plant can act profitably and deliver its bids and services. To achieve this, the framework considers multiple possible scenarios and receding horizon optimization. So this becomes an optimization with integer variables from the unit commitment problem, non-convexity from the optimal power flow equations, and a large size from the coupling of a 5-minute time step and a 24-hour horizon that could be difficult to solve in a tractable manner. So we split the optimization into 3 optimizations. So we have the high-level optimization, conducts a day-ahead unit commitment problem using a linearization of the OPF equations, making it a mixed integer linear problem with a 30-minute time step and a 24-hour prediction horizon. And this schedule is then passed down to the mid-level optimization. So the mid-level optimization conducts a preliminary economic dispatch problem with a 30-minute time step to attain an optimal use of storage over the coming 24 hours. Because the value of the integer variables was set at the high level, this is now a continuous optimization. And so we can use a second-order cone relaxation of the OPF equations to more accurately consider reactive power and network voltages. And this preliminary dispatch is then passed down to the low-level optimization. And the low-level optimization conducts a binding economic dispatch problem with a 5-minute time step and only a 30-minute prediction horizon. In this optimization, deviation from the mid-level preliminary dispatch is penalized. In this way, even though the low-level optimization has a short prediction horizon, its dispatch will remain close to the optimal operation that considers a 24-hour horizon. The low-level problem deviates from the preliminary dispatch, either to ensure the feasibility of the optimization or if there is sufficient financial incentive. So the schedule is set once per day, but the mid-level and low-level problems recede every 30 minutes and 5 minutes respectively, so that they can utilize the most up-to-date information, helping to counteract the negative impacts of uncertainty. In this way, the framework as a whole maintains tractability while having the desirable properties outlined earlier. So in this work, we look at an electricity hydrogen virtual power plant. And so the high-level optimization is minimizing the cost of importing energy, utilizing devices, and curtailing load, while maximizing the revenue from upstream reactive power support, provision of FCAS services, and selling hydrogen. It does this across all 48 time steps in its 24-hour prediction horizon and across a number of scenarios. The optimization is subject to linearized power flow constraints, device active and reactive power limits, and device curtailment limits. For time-sensitive services, such as FCAS, the amount each device can participate is restricted by its ramping capability. Because it is unknown if or when these FCAS services will be called, it must be ensured that the devices have sufficient power, headroom, and footroom to deliver these services. If the device relies on energy storage, there must also be sufficient headroom and footroom in the energy storage to provide the service. This is one of the sets of the intertemporal constraints, along with device ramping limits, electrical and hydrogen storage constraints, and the unit commitment minimum uptime downtime constraints, which, along with many others in the optimization, utilize the binary variables for committed status. So then the mid-level economic dispatch formulation differs from the high level in 2 major ways. Firstly, there are no integer variables, as the committed status of variables has been set. And secondly, because of this, a more accurate second-order cone convex relaxation can be used to better model the reactive power flows and nodal voltages. This is key to providing reliable local network support. Also, because this is now a second-order cone optimization, a more accurate convex quadratic cost term can be used for device operation to replace the linear one used at the high level. And the low-level economic dispatch formulation is much the same as the mid-level, except that there is an additional term in the objective function which acts to penalize the deviation of the low-level dispatch from the mid-level preliminary dispatch. Also, the time step is smaller at 5 minutes and the horizon is smaller at 30 minutes. However, the penalty term provides the low-level optimization with a view of the daily optimal operation without burdening it with a large prediction horizon. This allows the low voltage optimization to the low level optimization to ensure that local network support over a short timescale and to alter the virtual power plant dispatch in light of short-term fluctuations of renewables or if there is a sufficient financial incentive. So this is the case study that we considered in the paper. The network and the devices that you see together make up the virtual power plant. This virtual power plant considers both electricity and hydrogen energy vectors linked through the electrolyzer, hydrogen open cycle gas turbine, and hydrogen fuel cell. Hydrogen is considered in this case study, and it enables the virtual power plant to conduct energy arbitrage. The market operators would see the virtual power plant as a single entity located at the grid connection point, and the virtual power plant operates in energy, FCAS, and hydrogen markets to accrue revenue. It also provides local network support by ensuring that nodal voltage and line and device thermal limits are respected. Also, if required, the VPP can respond to signals from the network operator to absorb or inject reactive power into the grid at the grid connection point. The operation of the virtual power plant was considered over 10 representative days across 2016 using historical data, a representative weekday for each season, a representative weekend day for each season, and a high price day and a low price day. So this is an example of how the virtual power plant controls devices in the network to provide local voltage support. Here we can see that the purple lines are the voltage magnitude of the local bus bar, with and without local voltage support. The blue lines reactive power, and the orange lines represent active power from a device at that bus bar. Immediately, it should be apparent that there appears to be only one orange line, and this is because the VPP can maintain this node's voltage solely through the use of reactive power. So if we show where the voltage limits are, it can be seen that when the virtual power plant is providing local voltage support, the nodal voltage remains within allowable limits. And without it, this node's voltage magnitude would violate both the minimum and maximum voltage constraints. And it can be seen that whenever the voltages in the two cases diverge, there is also a divergence in the reactive power output of the device. So this is an example of for a single device on a single node, but the VPP framework controls all the devices in such a way that this voltage support is achieved across all nodes in the network. Here we can see the flexibility maps for the virtual power plant at specific times throughout the day. These show the feasible operating region of the virtual power plant and show just how much flexibility these VPPs have when optimizing their operation. It can be seen that for the most part, when the VPP does need to change its output to maintain local voltage limits, it manages to do so through the use of reactive power control. In times A, C, and F, it can be seen how the operating point of the VPP shifts in the reactive plane whilst maintaining its position in the active power plane. This shows that the provision of local voltage support has little effect on the ability of the VPP to provide FCAS or wholesale energy. In fact, for the typical autumn weekday, providing local voltage support increases the VPP cost by about 0.6%. This graph shows the reactive power output of the VPP in the case where upstream reactive power support is requested versus when it isn't. In this case, it was considered that a price signal was provided to the VPP to incentivize injection or absorption of reactive power rather than requesting a specific amount. This is why the reactive power injection or absorption is not constant over the periods where the support was requested. The price provided to the VPP was plus minus $1 per megawatt hour, which acts to show how much flexibility the VPP has with limited impact on its economic performance. To put it in perspective, the VPP accrued about $70 for its upstream reactive power support, which is about 0.3% of the objective function. So the representative days were used to estimate the cost of providing the local voltage support across all of 2016, as in the optimization, this is a constraint rather than a cost. There was no reimbursement considered for the service. So it can be seen from the graph that the cost of providing the local voltage support accounts for an increase in cost of operating the virtual power plant of around $250,000 across the year. It should be noted here that without the local network support, the nodal voltages range from 0.88 to 1.19 per unit, rather than the 0.95 to 1.05 when local voltage support is provided. Not only are these voltage deviations large, but also relatively frequent, occurring around 8% of the time. Also, revenue from the load that is being supplied by the VPP is not considered throughout this economic analysis. To put this in perspective, throughout 2016, the VPP would have to provide about 50 gigawatt hours of energy to the distribution substations above that generated by the renewables in the VPP. And if this energy was bought at wholesale price, it would cost energy distributors about $14 million. So active power curtailment events are rarely required, but coincide with high price events, which means that the amount of revenue that is lost through provision of this service can also be quite high. For example, the high price day accounts for approximately 95% of the lost revenue from the 10 days that we considered. So the VPP operating framework proposed in this work can effectively schedule and dispatch devices to operate in multiple markets and provide multiple network services whilst considering uncertainty. The local voltage support the VPP provides has a major impact on the voltage profiles in the local network. Most of the time, services such as local voltage support and upstream reactive power support can be provided without impacting on VPP revenue, thanks to the VPP's high flexibility, through prioritizing reactive power control. The few occurrences where active power control needs to be used to provide these services are usually during extreme pricing events, which are times when the VPP stands to accrue a large amount of revenue. But even so, the VPP could provide a cost-effective solution for local network support whilst maximizing profit. Thank you very much for listening. I will take any questions you have.
Thank you, James, for the presentation. There is a question from Nawaf. It's about second-order current relaxation, saying that it often fails under reverse power flow conditions, particularly when you have lots of renewables and all that. Did you notice anything like this in your simulations?
No, I didn't notice failure in reverse power flow. The only times where there were potential issues with the second order cone relaxation was in during periods where there was negative prices in the wholesale energy market. But by adding a term to penalize excess current or power flow in the network helps to tighten up that the relaxation. But no, I didn't see any issues regarding during times of reverse power flow. No.
Thank you. There is a question from Dan about essentially the virtual power plant geographical resolution, because it says it's all concentrated with one connection point, so everything downstream is basically one VPP. Any thoughts how you would do this if the virtual power plant would be spread over a large area, and effectively there would be different virtual power plants, and some parts would not be part of the virtual power plant? How would you do that?
Yeah, so I mean, the general concept of having a more spread out virtual power plant, having multiple power plants, the general concept of operation is the same. The difference becomes when you're providing things like this local network support, this voltage support. Now, obviously, in this case, this is kind of an idealized case where this virtual power plant is more or less taking the role of a distribution system operator, ensuring the feasibility of this distribution system. Of course, in reality, these would be two separate entities, and there would be some form of interaction between the two of the DSO procuring this service from a virtual power plant. So the way that economically the modeling would be very much the same. technically, when you have multiple virtual power plants more dispersed, you need to put more focus on the interaction between the virtual power plants and this kind of DSO entity.
Basically, the modeling framework would be sort of could cater for that.
Yes. Yeah.
Yeah. Yeah. Thanks. So there's a question from Mats. It says that this work reminds him of a set of networked energy hubs that would be interconnected by AC network. So are somehow VPPs the new energy hubs, and how do you see this?
Yeah. So the modeling of the individual nodes is kind of based on that kind of power energy hub concept, recently expanded by some of my fellow authors into kind of a multi-energy hubs in a recent paper, and it is that concept. And in this work, it is essentially networked energy hubs, but they're only interconnected by the electricity network. And obviously, to expand this work further and to make it more comprehensive, would be looking at some of the other presentations presented in this session, would be interconnecting these multi-energy hubs through, as you say, through multi-carrier networks to expand its how and when it can be used.
Okay, thanks. Just there's a follow-up question, and then unfortunately I have to close this very nice session. This is about the penalization you mentioned about the current term. So were we able to determine how large a term should be relative to the negativity of the price? The more penalty you would put on the current term, the more suboptimal your solution would be.
Yeah, so I found that as long as the weighting of the penalty term was larger, just it only had to be a small amount larger than the negative price, then it counteracted it sufficiently tightened the relaxation.
Okay, thank you. And I'm sure we could go on with lots of questions, not only for yourself, James, but for everyone. I really enjoyed, given a number of questions and everything else. I think everyone enjoyed. So let me thank you again, James. And I would also like to thank everyone again. An applause from me to everyone, all the speakers. Great presentations, great session. I would also like to thank the attendees. It's becoming very late in Europe. It's now become morning here in Melbourne. You can see the sun getting from my window. So I guess we will all go now to different paths. But it's been good to meet at least virtually, and I really hope the next one would be a physical meeting. So thanks everyone again, and yeah, have a good continuation of the PCC. Thank you.